Okay, so my next project for interfacing the TI-99 for a computer is going to be to control a slot car on a racetrack to compete against a human player. Now, this is something I've wanted to do for a while now, and after mulling it over for a few weeks, I figured it's worth a try, and I have a few ideas on how to achieve this. So the basic problem here consists of two issues. One is, how does the computer know where the car is on the racetrack? On which segment of the racetrack is the car located at any particular time? And second, how do we control the speed of the car in order to be able to manage curves, etc., and not fly off the track? So we're going to talk about these two parts separately. I'll show you the initial testing that I've done, and then we'll go on to show you the complete project. So for the first part, which is sensing the location of the car on the track, there is really no need to know the exact location of the car at any one time. What is important to know is on which segment of the track the car is. What I mean is, really, especially for when curves that are constant rate of turn, really I don't need to know where on the curve the car is. All I need to know is where does the curve start and where does the curve end. So if I put sensors at these two locations here, for example, when the car crosses the first sensor, I know it entered the curve. When it crosses the second sensor, I know it exited the curve. And with that information, I can adjust the car speed to safely maneuver that curve. Same thing goes with straightaways. You know, one sensor here, same sensor which really exited the curve, and another sensor to indicate the next turn will basically tell me that we're in the straight, and then adjust the speed accordingly. So that's what we're going to do. This is a track that I picked primarily because it is a very simple and cheap track that still offers some challenges as far as curves. It's an S-curve instead of just a regular oval. I'm going to go ahead and implement sensors at the beginning of each curve and at the end of each curve. So that's two here, and one at the start location here. So here's a piece of track that I'm going to test the sensor system on. What I've done is I have installed a photoresistor, which you can see over here, hopefully, through the track. And what I've done is basically just drill a hole down here and super glue the photoresistor on the bottom. And the circuit itself is a very simple circuit. If you look at this here, sorry, this is a very crude electrical drawing, but basically this is the photoresistor right here, and it's connected on one end to 5 volts and on the other end to a resistor and then to ground. The signal that will go out from that to the computer is taken from here between the resistor and the photoresistor itself. So when the photoresistor is fully lit, what happens is the resistance in the photoresistor is very low, and therefore the connection point here to the parallel port in the TI is connected directly to 5 volts, because there's really little resistance here. However, if the photoresistor is covered, say when the slot car is over it, then the connection to 5 volt is severed because of the high resistance of the photoresistor, and therefore the that connection goes to ground. It has nowhere else to go. And these are the two signals that basically we're going to use to detect whether a car is present or not on a particular spot on the track. If the line is high, that means that the photoresistor is not covered and the car is not present. If the line is low, that means the car is on top of the sensor, the photoresistor, and we know exactly where it is. Each of these, there'll be 6 of these photoresistors throughout the track, and each line will go to a single data bit on the 8-bit data port of the parallel port on the TI. So I can check each of these data bits, and if it is low, that means there's a car on a particular set of track, and if it's high, there is none. So what I did is I wrote a very quick and dirty assembly language program to test that. And what will happen is when I energize the circuit, it will detect whether a car is present or not and say so on the screen. This particular circuit with the car in place is connected to the parallel port through a parallel port cable. Right now we are connected. Oops, this thing fell out here. Let me fix that. There. Okay. So the photoresistor output line is connected via the parallel port to the pin number 1 right now as a test of the PIO port, and the ground of the PIO port is connected to the common ground of the circuit. This whole circuit here is energized by an external 6-volt power supply. In the real circuit, the powering will be done through the track power supply itself. In this particular track, it's a battery operated one with 4.5 volts, which should work just fine. So right now the circuit is energized and there's really nothing happening on the screen. The photoresistor is right here, so if we move the car over it and we look, and there we go, it says car detected. And if I move the car back, whoop, it goes away, move forward, back, back. So clearly the circuit works and the scheme works. And so what we're going to do is we're going to have each section of track equipped with a photoresistor, just like we did here, and they'll be connected to a separate pin on the PIO port of the TI, and we'll be able to tell where the car is. Alright, so next will be the test of the speed control for the car. Right, so the first thing we need to understand is how the speed controller for the cars work for this particular track. And this is essentially the same mechanism as for all slot cars generally. What we have is this little handle with a push button on top. Okay. When it's fully up, the car doesn't move at all, and then as we press it down, it starts accelerating gradually. When it's fully pushed down, the car is at maximum speed. Okay. This is connected to the track via these 2 prongs. Basically, what this is it's a variable resistor. When the button is fully up, the resistance is essentially infinite, and so no voltage is going through to the car, and it doesn't move. And then as we depress the button, the resistance gradually decreases until it hits about 0 or so at maximum depression. And so the car gets maximum voltage and goes at maximum speed. So So that's part one. So one way to control the circuit via the Texas Instruments computer is to use the cassette port through the cassette cable over here, and using only the cassette motor control plug right here, which turns the motor on the cassette deck on and off. This is actually acting like a switch when it is activated. And the way we do this is we connect the tip of the plug to the positive power supply of the circuit we're interested in. And what I've done here is the shaft of the plug is connected to a simple NPN transistor. Here it's a 2N2222, which controls the base of the transistor. The emitter is connected to ground, and the collector here, which will essentially pass current only when the base is negative. And this is connected to a solid state relay instead of a mechanical relay. The reason I'm using a solid state relay, even though they're a bit more expensive, is that they don't have any moving mechanical parts and therefore do not have any wear and tear, and they're very fast in switching, and there's no bounce either. Since the circuit we're going to be using will be switching on and off these relays very fast, I thought this would be a good choice. So anyway, the collector connects to the negative pole of the input of the relay, and the positive pole of the input goes to the positive power supply. The output side of the relay is the switch, which in this circuit, as a demonstration, I have it connected to an LED. Okay, and so when the switch is activated, the LED will turn on. I've written again a small assembly language program which activates the cassette motor plug on or off by me pressing on a key on the keyboard. And when this happens, then the LED will turn on and off. So if I press a key here, the LED turns on. Press a key, the LED turns off, and so on and so forth. So basically we are able then to provide some element of control using the cassette port. The problem is, as you've probably realized by now, this only switches the track to full on and full off. There's nothing in between, and clearly we cannot run the slot car at full speed because it'll fly off the track as soon as it hits a curve. So how are we going to control the speed? Well, one way of doing it is basically to vary the frequency of turning on and off the relay, so that the higher the frequency, the faster the car will go, because it will be in an on state more frequently, and vice versa. When the frequency is low, it will go slower. This will mimic a variable resistor, just like what the slot car speed control handle does, except it's not a resistor, it's just a variable frequency wave control, I should say, or pulse control. So next we will test this on the live circuit once I've assembled it, and we'll see how it works. So here I have the basic track set up, no frills at this point, just to demonstrate the property of pulse frequency modulation, which I'm going to be using to move the car on the track. So this is the same circuit we just talked about here. and I've written again a short assembly language program, and what it will do here, it will run the car on the track in slow motion, which means that you'll be able to see what I mean by pulse frequency modulation. The car will move in small incremental steps. This is obviously not going to be the final speed. This is just to demonstrate the concept. So here we go. I'm going to press a key on the keyboard of the TI, and you'll be able to see the car do that pulse frequency modulation function, where basically the car is powered by small pulses at a time, and by changing the frequency of the pulses, I'll be able to make it go faster or slower. So here we go. Power on, and there we go. So you can see it moving in discrete steps. Like I said, this is not the final speed, this is just a demo, but you get the concept basically how it's going to go. So if I increase the frequency of the pulses, the car will run much more smoothly and obviously faster. So next I'm going to show you the car running at a more normal speed. So here's another run, this time at a faster speed. I still cannot run it too smoothly yet, because it will fly off the curves, especially on the descending one, and all this will need to be tweaked in software in order to achieve variable speed depending on where on the track the car is. So I'm going to go ahead and press the key on the keyboard here, and you'll see the difference. And as you can see, it's definitely running much smoother. But like I said, I mean, there is definitely some software tweaks here to be done in order to improve the smoothness and maximize the speed depending on where we are on the track. So that's it for the proof of concept for motor control for the car. Next step will be to connect all the photoresistors in the track to the computer, and demo how the computer will be able to tell where the car is on the track. So here's a test with the full circuit and the sensors, as well as the motor power control, all connected to a PCB that I created. It's essentially the same circuit that I demonstrated earlier, except it's all combined on one PCB. We have a battery pack over here. We have an on-off switch with an LED to indicate power. Over here is the solid-state relay. This is the plug that connects to the cassette motor control on the cassette cable on the computer. Over here is the peripheral I/O port, which connects to the RS-232 parallel port on the computer, and over here are basically the pins that connect the photoresistors to the track. It's kind of a rat's nest of wires, because you have wires coming off from all the sensors over here, etc. There are essentially 4 zones on the track. We have Sector 1 over here, which is the beginning of the first curve, Sector 2, which is the first straightaway, Sector 3 is the second curve, and Sector 4 is the last straightaway, stretch before the finish. And each sector starts with a photoresistor, like here for Sector 3, here's the photoresistor. Sector 4, here it is over here. Sector 1, it's over here, and Sector 2, it's right there. There's also an a photoresistor right here for the player car. Basically, I would be using that in software to count the number of laps the player has had so far. Now, this track does have a lap counter on each side, but it'll be nice to have it also in software as well. So this test here will combine everything together. It's not optimized for speed. It's just going to show how the car responds to the different sectors by changing its speed. Subsequently, I will optimize the speed via software in order to make it more competitive for the human player. So over here is the program, which is now waiting for me to press a key to start the slot car control. So here we go. I'm gonna go ahead and start the power over here, and that gets the car going. And as you can see, notice how it accelerates and decelerates over certain zones. And we can see over here the zones that are being detected. 1, 2, 3, 4. So this detection system seems to be working really well. And you can see the car decelerate here for the curve, accelerate, move around, decelerate again, etc. So clearly it's still suboptimal as far as speed. Whoops. And it still has some bugs. What's happening here primarily is that because the car is moving at a low frequency modulation level, every time the motor starts on the car, it kind of jumps a little bit, and it actually can jump sometimes hard enough to get off track, which is what happened here. Once I increase the frequency, these jumps will be smoothed out a little bit, I hope, and so will make the car more reliable. Alright, so next stop will be the full speed demo. So here's the car optimized for speed. This is the best I could achieve at this point while being able to keep the car on the track consistently. It's been fairly tricky, and this is the result of many trials with different values and delays, etc., in order to get it to run consistently like that. So it's actually pretty good here. However, what I noticed is that with this particular track, the way it's designed, it's a really cheap track, is that when I use the controller to control the red car, which is the player car, the computer-controlled car slows down significantly. I think the design of the circuit is that there's power sharing, and it's just taking power away from the computer-controlled car to power the red car, which is the player car. So if you watch carefully here, I'm going to go ahead and start these, and you can see that the computer car has slowed down significantly. Now if I let go of the red car, the computer car accelerates, and if I go start the red car again, and you can see it's definitely slower here. So that's kind of a bump. So in the end, I decided to power each track separately, with the player car being powered by the onboard battery pack that comes with the track originally, and the computer-controlled car powered by a separate power supply seen here. And that obviously solves the problem completely. So why don't we see how this works? I've got the car optimized as best as I could to keep it on track as reliably as possible. Occasionally there are glitches, primarily related to the car, to the computer missing the detection of a particular sector, and so the speeds become off and the car can't fly off the track. But let's give it a shot. Okay, we're ready to give it a full trial here. I'll be controlling the red car with the controller, and the silver car will be controlled by the Texas Instruments computer. I'll go ahead and turn the power supply, and things will start very quickly. There we go. Oh, sweet. Alright, one of our first accidents here. And this one went off the track too, so... I'm having a hard time controlling the red car here, so here we go. So it's not as, actually it's hard to compete against the computer controlled car. As you can see, it's overtaking me. I'm going to try to concentrate here some more. But, yeah. I'm getting my ass kicked here. Oh, I went off track again. So the final product basically will have a lap counter on the computer to keep track of where each car is, because right now it's completely messy. Seeing here, hey, I may be able to, oh, it's catching up with me. Yeah, it's really not that easy. So the computer controlled car is really performing well here, as you can see. Alright, or I'm a lousy driver, whichever way. Probably the latter. In any case, so the project is essentially complete, and all I have to do now is just tidy up the interface and create a lap counter in software, and a countdown timer, so that you know, the cars start after a certain countdown, so that I don't have to coordinate pressing power buttons and such. Alright, I hope. So here's the interface, which is the final version. It's really a very primitive piece of software, just designed to demonstrate the bare minimum of the track. There are no really fancy features here. So we're gonna go ahead and do a full run, and you see on screen what's going on as far as the car location, etc. I'll be controlling the red car as I've shown before, and the computer will be controlling the silver car. So get things ready. So we'll start the countdown. And off we go. And as you can see, the tracks are being tracked. And I've hard-coded a limit of 20 laps. You know, I could eventually have it as user input, but for now this will suffice. So let me see if I can win here. Where am I? Okay, so I'm just behind. Oh, I went off track a little bit here. Okay, I have to make up for it. Damn it. So close. Anyway, so this is really the final version, and I hope you have enjoyed this project. Thank you for watching.
We do everything and us not go through them the other way around.